This video accompanies Learning IoT with Python and Raspberry Pi. In this video, you'll learn about the runtime complexity of the Heapsort algorithm.
The build heap function performs n divided by 2 push-down function calls, where n is the number of items in the list. The running time for the push-down function is on the order of hi, where hi is the height of the tree at the node at index I in the list. The highest node is at the root of the tree and is on the order of log n. Thus, the running time for the algorithm is on the order of n log n. The maximum number of iterations of pushdown during the process of building the heap is the sum of the height of all of the nodes in the tree, thus the order of n. The worst case running time is the order of n log n. A random sequence of integers was generated and then sorted. The running times were measured on the Raspberry Pi Model 4B. The Raspbian operating system was running a kernel version 4.19.50-V71 Plus. The Python code was run with the Python IDE and used Python 3.73. Let's open the Heapsort code and save this as Heapsort_timing, since we'll want to modify this code in order to time the execution of the Heapsort algorithm. From the random module, we'll import randint, since we need to generate a list of random integer values to be sorted. From the time module, we'll import time, since we need to time the execution of the code. I removed the print list function, and I'm removing all of the calls to the print function. We only want to time the execution of the algorithm. Let's create a for loop where we'll go for the size in range 10,000 to 100,000 in steps of 10,000. We'll create an empty list, hlist, and append onto the list values in the range of 1 to 9,999. Thus, we'll have a list of random values. We'll call the time function and store that value that's returned into start, and then we'll call the hsort function, passing in hlist as the argument. Once we return from the hsort function, we'll again call the time function and store that value in end. The duration is going to be the end time minus the start time. We'll print out the size of the list that was sorted and the duration. We'll clear the list before we go to the next iteration of the loop, and we want to run this for lists of size 10,000, 20,000, 30,000, 40,000, 50,000, 60,000, 70,000, 80,000, 90,000, and 100,000. As this plot illustrates, the runtime complexity is on the order of n log n. Let's look at the runtime complexity for several different sorting algorithms. The straight insertion sort, binary insertion sort, bubble sort, quicksort, and straight selection sort, as well as the heap sort, do not require any additional auxiliary memory. The merge sort, radix sort, bucket sort, and count sort have comparable or better runtimes than the heap sort. However, auxiliary memory is required when these algorithms are implemented.
Go to www.learningiot.net for information on where you can buy Learning IoT with Python and Raspberry Pi.